My favorite thing about the JASON project is getting kids out into the field and getting them hands-on, having them interact with different scientists, learning things that they would not have an opportunity to learn while they're probably at school.
Well, it's always interesting to watch the students begin to grasp new concepts or to find something that they haven't actually seen and practiced before. Maybe they've only read about in a textbook.
My favorite part about the job is obviously working with the JASON Argonauts. We've been with the JASON and the Argonaut program for 7 years. It's a wonderful program to get kids interested in science, technology, math. Sometimes they don't understand that you can't do science without math, or the technology's great, but you really need to know the basic science behind it before you depend on the technology. So we have lots of wonderful school kids that come out, and we just love working with the different groups of students.
About 8 years old, I discovered the night sky, and where I lived in southeast Texas, there were no street lights, so I actually got to see the Milky Way at night, and I decided I wanted to be a part of the space program when it got started during Apollo, and I did become part of the space program. I got to study lunar samples, then I went from at Rice University, and then I went from Rice University to Max Planck Institute for Nuclear Physics in Heidelberg, Germany, where I did the same thing for 6.5 years. So it's been just a passion of mine for quite a number of years to understand the Earth and as well as space as well. In fact, the entire solar system has been my interest for quite some time. I got my bachelor's degree at Lamar University, and actually Apollo took off in the years that I was at Lamar. And right as soon as I left Lamar University, I went to Rice University. And you know, the bachelor's degree at Lamar was really helpful, and in fact I did well at Rice and went on from there to Germany. So I feel like it was a good background to have.
You know, Lamar has a very good biology department, and they also have a good library. I always say, if you can think of a problem, a thesis problem, once you think of it, you need to go to the library next and start looking at the literature.
One of the things that I got used to as a student, and I never really lost, is my passion for these extremely long periods of time that I can't even comprehend. But nonetheless, we have ways and means of actually understanding time very well. And it was one of the most attractive things to me about the field of geology was this whole sense of antiquity. We no longer talk about just a few hundred years ago. We talk about 4.5 billion years ago or even more. So even though it's hard as a human to understand such long periods of time, it most definitely has been a big attractor for me.
I'm an undergraduate at the university. I work for Dr. Jordan. I'm glad I made that choice, obviously. I mean, we need as many scientists as we can get, and sky's the limit for careers, both academically and privately.
The best thing about teaching geology for me is being able to get paid to go out to beautiful places like this.
If anybody wants to become a park ranger, it's probably the best job in the world. We do everything from science to history to all of the different ologies. If you worked at the Grand Canyon, you'd want to take some geology classes. If you work at Big Thicket, you definitely want to take botany and biology. So it sort of depends on where you want to work. You could pretty much have a degree in anything and get a great job in the National Park Service. The National Park Service has not only natural sites like Yellowstone and the Grand Canyon and Big Thicket National Preserve, but historic sites. So a person that's quite interested in our cultural history of our nation might want to take their history classes and work at George Washington Carver's boyhood home or the National Monument or the Mall in Washington, D.C. So there's lots of different avenues you can take.
We have a train coming which is called the STEM, which is Science, Technology, Engineering, and Mathematics problem, which is nationally becoming extremely important because we're running out of a workforce that in fact will be supportive of what our infrastructure is right now. We need to do something about bringing our students into science, technology, engineering, and mathematics fields. So it's a very promising future for those that are going into the science, technology, engineering, and mathematics fields. It's already beginning to show, and it will be in the future as well.
I'm retired. Oh, but I love Jason so much, I came back to continue with the training. What keeps me involved with Jason is I find this to me one of the most stimulating curriculums in science there is. What other curriculum promotes students meeting scientists and interacting with them and going out? Not only do we have local kids involved as scientists in the area, but the Jason program promotes it nationally as well. So that's why I like Jason. It's on the edge.
Welcome to the Lamar University and this year's Jason event, Immersion in Coastal Environments.
I'm Kendall Gibson from Bridge City Middle School and an Argo co-host.
I'm Gobin Cagle from Odom Academy in Beaumont and your other co-host.
Today's missions on coastal environments will begin with a trip to the Big Thicket to learn how to navigate with a compass.
Then, we will go to the Coastal Fisheries Lab on Pleasure Island to see creatures from the Gulf of Mexico's food web.
Next, we will see how sedimentary layers at Seagram State Park tell us about hurricanes that have slammed into our beaches.
Finally, we'll find out how a salt dome made High Island so high.
So let's head to the Big Thicket.
Welcome, Jason Argonauts, to Big Thicket National Preserve. Can anybody tell me what this is?
Compass.
It's a compass, that's right. And what do I use this for?
To directions.
To find my direction, to see where I want to go, to get out of the woods if I'm in the woods. What is this?
A GPS.
This is a GPS which works by what?
Satellite.
Right, by triangulation with satellites. And these are wonderful new technology. You can go all kinds of places and track your way back out unless something bad happens. What could happen that makes this useless?
Batteries die.
Okay, your batteries die. You forgot to bring backup batteries. What else?
The canopy. The stuff above your head is too much and you can't reach the
What'd you call it before? The
canopy.
The canopy. When we get back in the Big Thicket, the operative word there, sometimes the canopy is closed. That means I can barely see the sky through the tops of the trees. Sometimes that makes these difficult to use, especially on a cloudy day. So if you get way out in the woods and you're depending on a GPS to get you out of the woods, and all of a sudden you lose your signal, you could be just going in circles. You would have no idea. Or if they drop it in, this one happens to be waterproof, but if you drop in the water, the battery dries, a lot of things can happen with technology. So never ever go in the woods with one of these unless you have one of these. This will get you out. When you're looking at your compass, you have a base plate. That's the square on the bottom. Okay. Where it says direction of travel, and that's on your little compass, it's this arrow right here. Okay. That should always point away from you. That's the direction you're traveling. So it doesn't do you a whole lot of good if you're carrying it backwards or sideways. Okay, so that's your direction of travel arrow. Should always point straight out in front of you. Okay, the dial is the thing that spins around on the little compasses. It has a black ring around it that has the numbers on it. How many degrees are in a full circle?
360.
Excellent. And the arrow that floats is your magnetic needle. And what way does the red always point?
North.
Which way is north point? There you go. And you know it, you can read that right away. This is your floating arrow and it always points north. Within your dial, there's another arrow. Do you see that on yours? It's red on here, and it's also got some glow in the dark things, so you could actually use it at night if you had to. That is your bearing. That's the way you want to go. So, or that's how you set the way you want to go. So for the next activity, what we'll be asking you to do is to start at a certain point. We'll ask you to set your compasses at a certain bearing, and then we'll ask you to walk a certain distance. And that's just practice using the compass. The trick about using a compass to walk on a line is that you can't really walk like this and keep your compass steady enough, and it's going to move a little bit. So, for example, if I set my compass bearing on 30 degrees northeast, and I look in that direction, I'm seeing a little tree over there. So now I can put my compass down and count my paces walking towards that tree. And I know I'm going to stay on my line. I don't have to sit here and stare at my compass the whole time. Does that make sense? Now, how do I know how to go that direction? I set it at the degrees that I know I want to go, for this game anyway, and then I turn my body until the 2 red arrows line up. Sometimes in thick woods like this, your sight might be 20 feet and you have to take another sight. And then you have to take another sight. You just have to keep doing it by line of sight. Sometimes your line of sight is going to be very short in these woods.
Does the compass really point to the North Pole?
The compass points north depending on where you are. There's a thing called magnetic declination, and if you're really going to be going cross country and you need to be accurate, you will have to figure in the magnetic declination for your area. In this area, I think it's about 6 degrees, so we would have to adjust our compass. So we want to go due north. Instead of setting it on 0, we would set it on 6. Over miles, it's going to throw you off 6 degrees. 6 degrees over a mile is a long way. Over 300 feet, it's not that bad.
All over years, the magnetic field shifts. So will that, like in 200 years, would that affect the compass?
It won't affect the compass because the compass will consistently point at the magnetic North Pole. But as that magnetic pole shifts, it will be pointing a different spot. And so what we have charts that we can adjust for each year wherever the new position of the pole is, so we can compensate. And over about 10,000 years, it actually averages on the actual geographic North Pole. Okay. But right now it's up in kind of central Canada and not over the Arctic Ocean.
What kind of forces can change a compass, like weather or anything that can?
Weather, not so much. I know that when in certain areas where there's a lot of iron ore, that can throw you off, and you have to make compensation for that. Sometimes if you have a metal belt buckle, if you have, cell phones, that's why you need to kind of keep it away from things like that.
My favorite part was walking through the woods from point 27 to point 5 and ending up at the right spot.
I think it's very interesting. I've never been here before, so I kind of liked it. I learned how to use the compass and, find your way if you're lost in the woods or if you need to travel.
I liked going through the woods with my compass and being left to my own devices and trying to find my way to one trail to another.
Probably getting to walk through the woods in shorts.
If you wash yourself with detergent, it gets off the poison ivy.
Ducking and jumping and trekking through the trees.
If you don't have a compass and you're lost in the woods, and they said that there's somewhere that you can tell if there's moss on the tree, which way north or whatever.
Okay, I see moss right here. Is there any moss over there?
There's not on the top. There's not right here.
Not on the top, but look at the bottom.
Yeah.
And this, these are lichens. There's moss all the way around that tree. So that doesn't work really well here in Southeast Texas because it's so shady and it's so warm, and the moss grows all the way around the trees most of the time. That older way of orienteering works if you're somewhere further north where the sun is low in the sky and the southern sun hits that south side of the tree, which causes the moss not to grow there. But in Southeast Texas, not so much. Obviously the sun, and knowing, you know, where the sun rises, where does it rise? In the east and sets in the west. But in the winter it's further to the south, so you still have to kind of know where the sun is supposed to be in order to use that for your bearings. And the best advice for that is to always stay put. Tell someone where you're going, when you should be back, and if you find yourself lost, just stay where you are. We will come find you. Because if you keep trying to find your way out and you have no tools to work with, you're likely to just get further and further in the woods, and it'll just take us that much longer to find you. I never trust the moss on the tree thing, not in Southeast Texas.
Hey, I've got a question for you. Which of these tools is most dependable for navigating in the dense forest of the Big Thicket? Is it A, a road map, B, a GPS, or C, a compass? What do you think? The correct answer is C, a compass. And if you knew that, you're going in the right direction.
I'm a fisheries biologist for Texas Parks and Wildlife, Coastal Fisheries. We are one of 8 field stations on the Texas coast, and our job here on the coast is to monitor fish and shellfish populations, angler activities, and even commercial fishing activities. I wanted to discuss with y'all today was how important our marshes are. We wasn't given the gift of processing sunlight. Plants were given that gift through a chemical process called photosynthesis, the biggest driving force on this planet. Without the plants, without capturing sunlight, there's a lot of things that wouldn't happen. So our coastal marshes are very important to us, and it's important to the fish that you see in front of us, and many of those that are not in front of you. A lot of these fish, they're not designed to be feeding on plant material. But we have fish that are dependent on tidal food chain or plant material in some sense, and they're all dependent on the estuaries somehow, and going back to that plant energy, the photosynthesis. They're important to us for the food that they provide. Our marshes are very important. I cut some gill covers out of a few of these fish. This is a Gulf menhaden. This is a very large commercial finfish fishery off the Texas coast, especially on this end of the Texas coast. And here's the first gill raker on the left side. Now, the gill raker itself, the gill itself, has 2 surfaces, the filaments and then the raker side. I want you to feel this. You feel on the inside is the raker. This is kind of like bristles of a comb. But on the filament side, they're really hair-like, and this is what carries the blood and extracts oxygen from the water and gives up CO2. That's the breathing mechanism of a fish. But the fish ends up filtering the water as it comes across the gill, and it takes the rakers and it traps the organisms on the raker, and then he either sucks real hard or his tongue cleans the raker off. The material goes into his gut. Now it's y'all's turn. Who wants to do some cutting?
The main mission of our coastal fisheries labs is to monitor the health of the coastal food web and its fisheries. This requires special equipment like RVs or research vessels, and the equipment which is deployed from them. And that includes water sampling devices, cables and pulleys for dropping and lifting equipment, oyster dredges, and specialized fishing nets. The Gulf of Mexico food web is made of thousands of crisscrossing marine and estuarine food chains. Plants are the foundation of the web. Filter feeders like menhaden are a first stage in transferring energy and biomass throughout the web. Hundreds of intermediary carnivorous fish species and thousands of consumer invertebrate species pass energy and biomass upward through the web until it is finally transferred to apex predators like sharks and dolphins. Along the way, decomposers like bacteria convert undigested animal material back into plant nutrients, which allows the cycle to continue without interruption. Man has increasingly impacted this ecosystem as fishing industries have developed technology making humans super apex predators in the Gulf. And our shrimp-eating Argos are glad we are.
What's the largest predator in the Gulf of Mexico?
The top predator. Well, guess what, folks? You're looking at him. Man has used various tools to go after fish and to place their impacts across the globe. And he's done it in a number of ways. How about bow and arrow? How about rod and reel? You ever seen a party boat or a fishing pier with just one angler on them? No, you see fishing piers with hundreds of fishermen with lots of rods and reels. We are the top carnivores, and we can gobble food at any food chain better than anybody else. Better than great whites, better than bull sharks.
Do the bull sharks' mothers ever eat the babies?
Well, if they're sickly, they better not be showing any signs around mom and dad, because I have a feeling the weak ones will be targets for either mom and dad or their siblings. They're not precocial. They don't depend on mom and dad. They got to be able to swim and swim away with strength.
What's the most common type of fish that you catch here?
That's a good question. Depending on gear, time of year, I would say menhaden would be at the top of the list. They're at the base of the food chain, so their numbers are going to be naturally quite high.
When we took apart the gills and we took out a layer, if a fish had a smaller filament than another, would it have to breathe more times to get the same amount of oxygen?
The gill structure they have when they're only a few inches in length are appropriate for their size. And that size is going to change as they become bigger fish. A red drum 40 inches in length is definitely not going to have the gill arch the size of a juvenile or larval fish. And so they change with a body mass ratio to keep the oxygen consumption normal.
How long do manta rays usually live?
Let's think about their growth rates. When they're born, they're pretty small. And so they're quite large as adults. So to go from a small one to a large one takes many years. And I would say it should be a lot greater than 10 years. And so that I think they're long-lived for sure.
The stingray, why is its stinger shorter than the tail?
It probably has some evolutionary and defense mechanisms associated with it. So his tail is longer than the spine, probably as an alert mechanism of someone approaching, a sensory type deal. That would be from a biologist endpoint thinking about it.
Although we now see that the Gulf of Mexico's food web is very complex and is comprised of thousands of species from microscopic plankton to sharks and whales, it is also fragile. Humans have developed the technology to wipe out the fisheries we depend on for food and recreation. It is the job of fisheries researchers all along the coast to monitor the health of our fisheries and make sure we do not take more than the food web can replace. Hey, if you're ready for another question, raise your hand. Oh yeah, you're ready. Which of these fish gets food by filter feeding? Is it A, bull shark, B, stingray, or C, menhaden? The correct answer is C, menhaden, and there's nothing fishy about that. Our Argos ventured into a salt marsh at Sea Rim State Park to learn how sedimentary layers record hurricane events.
What we're looking at today is the marsh area of the Sea Rim Park, which has a different kind of sedimentation than you see on the beach. On the beach you see sand. Back here you see black mud. The black mud is because of all the vegetation you see. During storm surges, we actually see movement of the sand inland. And of course the sand looks quite a bit different. It's tan colored. It's also coarser grained. And so when we go down, if we see sand from any surge, we would see it as a light tan layer compared to a black mud layer. 2008, Ike came through and had a surge. We measured, I think, about 18 feet, so it did bring quite a bit of sand in. And in 2010, we actually were here and sampled and did see a sand layer beneath the black mud. So we're thinking we'll see the same thing today, we hope anyway.
All right. There we go.
Here we go to the rough part. Here we go.
Woo! No one ever said science. It's easy and or clean.
You'll see black, tan, then black again. And what we can look at and see, we know this sand was brought by Ike. So if we do deeper cores, and we do, and we see tan layers intermixed with dark layers, we can try to do the history of hurricanes that way. This is about, well, it's compacted a little bit. It's probably about 100 years represented here.
How do you date the time frame of the sand?
We came to this site 2 years after Ike surge, and we found that the black layer, how thick it was, and we knew that had been 10 years, 2 years, excuse me. And so we were able to establish what is known as a sedimentation rate. In any effort to determine how long these cores represent, we have to understand how fast the sediment was deposited. So we have techniques to figure out how fast that deposition rate is, and once we know that, we can tell you how old a particular thickness is. So right in the Texas Gulf Coast, one rule is that it's about 1 meter is about a century, and this is about a little over a meter. So we're going backwards in time the deeper we core. And we have done cores as deep as 9 meters just to see what we could find.
Does it matter where y'all do this, or did y'all choose this for a specific purpose?
Well, yes, it does matter. In fact, we knew from NOAA mapping and that sort of thing where all the surge waters were. So we naturally would decide to go to where the surge was. This is definitely one of those places. And well, again, what you look for is you look for organic type of sediments, which are black, versus sand stripes in the stratigraphy of the core, and that tells us basically that some surge phenomena brought that sediment in. In the case of Ike, we knew that, but in deeper portions of the core, it could be storms that were way before Ike. So, yeah, it matters. The marsh areas behind the beaches are the best places to look for this sort of phenomena.
How long has this been a marshal area?
It's been a marsh area for about 5,000 years. About 10,000 years ago, the beach was much farther out, and sea level has risen since then and has stabilized here about 5,000 years ago.
Are there any other places to core besides the marsh?
Yes, there are. Marsh areas are particularly good because of the black sediment. It gives us a separation of the color, which was useful. But we also can look into regions that have a lot of sand as well, but they may have, if we look at their fossil record or shell record, we may be able to distinguish between marine material and coastal material that's non-marine. We have rivers and streams that bring in sand, but that's non-marine. So it's quite possible that we can distinguish between one type of sand and another type of sand and determine that this is marine sand versus river sand. But that's more difficult because we don't have color to help us.
Did Hurricane Rita leave any sand deposits?
That's a good question. Actually, no is the answer, because the wind direction determines whether surge is coming in or going out. And so in this case of Rita, we had winds coming out of the north, and the rotation was different. So on the east side, where the rotation would bring in the water and the sand along with it, that's where you'd see surge effects, and that's what Ike did, but Rita was not. We were on a different side, and the winds were blowing in the opposite direction.
Why do you want to study old hurricane deposits?
Well, one reason is that if you look at the history of meteorology, the news that you see on television, you go back probably at best, very best, probably 100 plus years, maybe 150 years at best. So in order to know about hurricanes before that, You don't have any news reports. You don't have any reports whatsoever. So we look at the whole idea of doing an exploration of the entire Gulf Coast and taking cores along the way is to determine what kind of past hurricanes way before 100 years ago, perhaps even 200, 300 years ago. And so the only way we can do that is to look to these sediments. Why do we want to do that? We want to understand the Earth's processes. We want to understand what hurricane frequencies are, of different intensities of the hurricanes. And for our historical record, we don't have that much information. So we have to go to the prehistorical record by looking into these cores.
So geologists use beach sand layers deposited by hurricane storm surges to document recent and prehistoric hurricane events. By studying these storm deposits along the Gulf Coast, we may determine whether the frequency of tropical storms has increased in recent times or whether the occurrence of hurricanes has remained about the same during the 5,000 years.
It was interesting because I never thought someone could do that.
Core mining, that was pretty fun.
And just being here, it's fun.
I learned about the oxidation in the ground, how the black soil is because it has a lack of oxygen.
Were you paying attention? I hope so, because I've got another question for you. The salt marshes of the Texas coast have been in their present location for about how long? Is it A, 5,000 years, B, 5 million years, or C, 5 billion years? What do you think? The answer is A, 5,000 years. For our final immersion expedition, our Argos will explore High Island on the coast south of Winnie, Texas. There they'll discover what exactly a salt dome is and how it pushed High Island up above the local salt marshes.
We're here on or close to the top of High Island. Basically, y'all were down in the marshes near the base. Okay, what's different from up here?
There's trees here.
There's trees, that's right. There's trees up here in High Island. Because you're not down in the salt marshes, you don't have as much salt, okay? And these trees are able to grow a little bit better here. They're above permanent moisture, and they like to have aerated soil, so they're able to grow. Does anybody know why High Island is here?
Because the salt that comes in from the ocean evaporates and then it builds up slowly over time.
That's right. So what we have is basically, originally, the salt layer was called the Luan salt. And the Luan salt formed as the Gulf of Mexico was forming. And all the continents were together at one time, or at least most of them were together at one time. Around the Triassic period of geologic time, you started having a splitting apart of this Pangea. And as it split apart during the Triassic, you started getting some what's called extensional faulting and subsidence starting to occur. Now, it wasn't until 170 or 175 million years ago in which we started having the Luan salt actually come in and start form. And the reason for that is that the Gulf was then extended far enough and it was low enough that seawater from the surrounding oceans that were forming was able to come in and filter in into that area. Now, it was relatively dry at that period of time. So what happened was, as the seawater came in, it would start to evaporate. There's other things in there as well, but salt was the dominant product. And over a period of about 10 million years of basically the water coming in, evaporating, more water coming in and evaporating, you built up about 5,000 feet or so on average of this Luan salt. As the Gulf continued to form and continued to spread, you had limestone and limestone reefs that were developed on top of the salt. The marine layer came in and started depositing that. Then after that period of time, you had large amounts of sediment come in and pile into the Gulf, creating very, very thick deposits of salt. All of this pushed essentially the salt down to about 6 kilometers deep. And because the salt was less dense than the compacted sediments, because as you start compacting the sediments, they turn into sedimentary rock. You go clay and you've got sand, they turn into shale and sandstone. The shale and sandstone was denser than the surrounding salt. So it has what's called a buoyancy effect. You know, what happens if you take a ball or a beach ball or a balloon or something, bring it down under the water and let it go? What's going to happen? It's going to flow up to the surface. Why?
It's less dense in the water.
That's right, it's less dense than the water. Well, salt was less dense than the surrounding sedimentary rocks, and so it started pushing upwards. And as it did that, it would take the flat-lying sediments and would start pushing up on them and bowing them upward. Eventually, what would happen is that this salt would bow it up to the point and then basically pierce its way up and continue on up close to the surface. After striking oil and spindle top, then they mapped out the actual salt underneath here by drilling oil and gas around the 1920s. That's when they first discovered it near the top. And they drilled down beneath a little bit of the cap rock and the salt, and they actually produced oil and gas from the flanks. And in fact, it's that oil and gas from the flanks that is being produced today. Well, we're here at one of the oil well locations, and what I'm going to do is explain to you how geophysicists and geologists actually search for salt domes and search for the strata that is bent up around salt domes in which trap oil and gas adjacent to the salt domes. Okay? Now, when we look at layers of Earth, basically we can see very large-scale amplitudes and oftentimes very continuous amplitude variations. We have black called peaks, and the other lines in the other direction to the left are called troughs. These alternating troughs and peaks indicate where we have interlayered strata. Now, one area in which you want to look for oil and gas is where these layers are bent adjacent to the salt dome that is basically pierced these layers. The salt itself, which is indicated right through here, if you look just adjacent to it, particularly in this area, you can see how the layers are coming through and all of a sudden they are bent upwards adjacent to the salt dome. The oil moves up, it's trapped against the salt, and it can't move past the salt anymore. And so you try to sink oil and gas wells to try to penetrate through here and pump up the oil and gas from these more porous rock units, usually the sandstones. The more porous rock units, they pump out the oil and natural gas from. Okay? And that's how we look for these things through here. Now, there is another way in which we can look for these salt domes. Remember, we were talking about salt. The reason it moves up is why? What is it's less dense than the surrounding rock layers. Okay. Now, there's another way to look for it, and that's through the measurement of gravity. If there are less dense rocks in the subsurface juxtaposed to more dense rocks, the gravitational attraction is going to be less, and we'll have a gravity low. If we have more dense rocks, then we'll have a gravity high. Now, the interesting thing is that before seismic, salt domes were actually found by looking for these gravity anomalies. What you see actually is that you have some denser rocks that are thinner but very close to the top. These denser rocks are the anhydrite. Okay? The anhydrite are much denser than the salt. And they're also denser than the surrounding areas. So when the anhydrite comes close to the surface and the limestone cap rock, it actually gives you a little gravity high. So what you would see is if we plotted gravity on here, as we got closer to this salt dome, you might start seeing a gravity low coming down, and then right over the top, if there was a cap rock, you might see a little gravity high, and then back down to a gravity low again as it goes through. So it was actually gravity was first used to help identify where salt domes are, where the margins are, and where we should actually drill. Well, what we are standing next to is oil and gas pump jack. These ring High Island. And the reason they do that is that they are drilling down along the margins of the salt or just along an overhang in the salt. Once they drill down and hit this, oftentimes the oil and gas is underneath enough pressure that what happens is that we actually have it rising to the surface naturally. But over time, the pressure decreases. And so what you have to do is you have to actually pump that oil out. Now, when it comes to natural gas, which is what a lot of the wells are being drilled for now, once the pressure is reduced, it's no longer useful. It has to come out naturally. But for oil, oil is worth enough money that you can still pump it out. Essentially what's happening here is that you have a weight, and that weight is a counterbalance. At the top you have what's called a sucker rod, and the sucker rod goes on down into the well, and it has a valve on it. The sucker rod goes down, the valve is open, and it allows oil to flow in. When the sucker rod goes back up, it's actually pulling that oil up, and it's flowing into this pipe. That pipe then takes it out into some storage tanks. It eventually then, the oil trucks will come by, offload this from the storage tanks, and take it away. Sometimes if there's enough oil, it'll go directly into a pipeline.
So that's how they drill for oil. So far we've learned how High Island was formed and the benefits that the salt dome offers us all. But what about High Island's natural inhabitants? How does mankind affect their environment?
Okay, this is just a quick fun stop here. We're at the Smith Woods Waterbird Rookery. This is managed by the Houston Audubon Society. And whereas usually industrial activities are disruptive to animals, this is an example where humans disrupted this environment, but in a positive way for the water birds. So this is an artificial pond that's diked out and an artificial island out in the pond, and the birds are nesting on the island. These birds actually can fly underwater. These are called cormorants, and so they hunt for fish underwater, unlike a lot of the egrets and herons that you see wading and stabbing fish and crabs. These guys actually fly with their wings and catch the fish. And right now it's a little bit too cold, but usually we have alligators surrounding the islands. Any idea why alligators would want to hang out around this island?
To protect the birds.
Well, by being there, they protect the birds. What would they be protecting them from?
The raccoons, possibly.
Yeah, why might raccoons want to get on that island?
The baby birds.
Yeah, eat the baby birds and the eggs, and same thing with snakes and possums. And so what would happen if a raccoon decided it was going to swim across to the island?
Then the alligator would kill it.
Yeah, the alligators are going to catch most of the predators that are trying to invade the nesting area. When you have thousands of babies, a lot of them don't make it. So there's what's called high infant mortality for baby birds, and the alligators eat those babies that die. And so they get paid to protect the rookery. And they also are, in that case, janitors too, because they clean up the dead bodies and make it a much healthier environment. And you guys all know about Nemo fish and sea anemones. What's that relationship called?
A mutualistic relationship.
Yeah, a mutualistic relationship. So who benefits between the alligators and the birds here? Alligators, what about the birds? Yeah, the birds too. Yeah, so they're helping each other out. So it's a great example of a mutualistic relationship in the coastal environments as opposed to out on the coral reefs. The biggest threat to this ecosystem is people, but now the Houston Audubon Society is managing it. They're keeping people from hurting the animals. The second biggest thing is lack of water. And with the drought a year ago, this water levels almost dried up totally. So that's the biggest thing. The good news is that they can artificially add water, and that's what they did this last year. This used to be an Amoco oil company facility, and when BP bought Amoco, the refinery that was Amoco and down by Galveston is now BP refinery. When they bought it, they gave up the property, and that's when the rookery started actually functioning very well because people weren't here to disturb the birds. And so having humans protect the alligators and the birds made a very good habitat for them to come to.
Coming into today, I didn't know about the hot islands, so there's one thing I learned about, and I learned about the salt domes.
Push the island up, making like hills and trees and all.
The oil people found the salt domes when they were trying to find oil.
I learned that birds and alligators have a mutualistic relationship.
The alligators and birds work together to survive out here.
My favorite part was getting to see all the birds and hearing the noises and hearing all their sounds they make.
Just experiencing all this, getting to meet new people, learning about all of it.
Getting to see High Island and how it's raised up over everything else and all the trees and everything.
I don't know, I guess meeting new people because, I love this whole thing.
It's time to find out who knows best with another question. Here it is. Which of these geologic resources do we not get from salt domes? Is it A, oil, B, natural gas, C, gold, or D, salt? Think it over. The correct answer is C, gold.
Thanks for coming to this year's JASON program.
Remember, JASON needs Argos like you for national JASON missions.
If you would like to apply to be a National Argo, visit the JASON website at www.jason.org for details.
And be sure to come back for next year's JASON event on oceans and climates.